share with you the detail of the hydraulic fracturing process so that you know why it is, without any shadow of doubt, that this ain't a particularly good idea and we do need to kick these frackers out. So I'm going to start by showing you a short animation. It's an animation that's actually produced by one of the gas companies working in the Utica Shale, which is actually the northwestern part of the Marcellus Shale, but just over the Canadian border. Now, obviously it's a promo video. It's the Canadian company demonstrating that, they're up for the job, that they understand the process, that it's clean, it's safe, and just listen to the narrative, because it'll start to give you an idea of how they very carefully choose their words. So they're not lying, but they're not necessarily exactly sharing the whole truth either. So this runs for just about 5 minutes. And then what I'm going to do is we're going to break the narration down so that you can see the, if you like, the deception and the obfuscation. So here we go. This is the Utica Shale.
Natural gas from the Utica Shale is a clean and efficient energy source that is abundant in the St. Lawrence lowlands of Quebec. Let's take a look at the horizontal drilling and stimulation processes that have made shale gas exploration so successful. A drill bit is mounted on the end of the drill pipe. As the bit grinds away, a mixture of water and additives called mud is pumped into the hole to cool the bit and flush the cuttings to the surface. The mud cakes on the walls of the wellbore, keeping it intact and preventing invasion of drilling mud into the surrounding rock formation. The hole is drilled below the deepest freshwater zone or aquifer near the surface. The drill pipe and bit are removed. Surface casing is then inserted into the drilled hole to isolate the freshwater aquifers. Once cemented, it serves as a foundation for the blowout preventer, a safety device that connects the rig to the well bore. Cement is pumped down the casing and out through the opening of the shoe at the bottom of the casing. It is then forced up between the casing and the hole, permanently sealing off the well bore from the fresh water. Once the blowout preventers are installed, the pipe and bit are lowered back down the hole to drill through the plug and cement and continue the vertical section of the well to approximately 300 meters above the planned horizontal leg. This depth is called the kickoff point, where the curve will begin so that the horizontal section can be drilled. Up to this point, the process is the same as drilling a vertical well. Again, the pipe and bit are pulled out of the hole, and a downhole drilling motor with measurement while drilling instruments is lowered back into the hole to begin the angle building process. The distance to make the curve from the kickoff point to where the wellbore becomes horizontal is typically just under 300 meters. Once the curve is completed, drilling begins on the well's horizontal section called the lateral. The pipe used to drill the well measures 9 meters in length, and each length weighs approximately 224 kilograms. It takes over 350 pieces of pipe, weighing nearly 79 tons, to drill a 3,200 meter well. At various stages of drilling, the pipe is taken out of the hole for tool and bit changes and put back in. This process is called tripping pipe. When the targeted distance is reached, the drill pipe and bit are removed from the wellbore one last time. Production casing is now inserted into the full length of the wellbore. Cement is again pumped down the casing and out through the hole in the casing shoe, forcing the cement up between the casing and the wall of the hole, filling the open space known as the annulus. Casing the well is a very important process because it permanently secures the well bore, and it prevents hydrocarbons and other fluids from seeping out into the formation as they are brought to the surface. At this point, the drilling rig is no longer needed. A temporary wellhead is installed, and the location is prepared for the service crew, who will perf, frack, and prepare the well for production. The first of these steps is to perf or perforate the casing. A perforating gun is inserted into the casing to the targeted section of the horizontal leg. An electrical current is sent down the wire line to the perf gun and sets off a charge that shoots small holes through the casing and cement and out a short distance into the shale formation.
Now, if that was the end of the process, that would ostensibly be a conventional well. So when you hear protagonists for fracturing say, but the process we're using is exactly the same as for a conventional well, they're not actually lying. But neither are they telling you the whole truth, because the process in unconventional geology isn't finished. In a conventional well, having perforated the casing and the cement and opened the well to the geology, whether it's water, oil or gas, if it's conventional, then the natural pressure of the water, oil or gas in that reservoir will find the path of least resistance, which is now the perforations. It will come into the well and it will flow to the surface. Now there's some 2,000 or so conventional wells that have been drilled in this country for oil and gas. And as far as we're aware, without any major issue. And untold number of water wells, and it's the same process. But this is unconventional geology. And it's called unconventional for a very good reason. It's otherwise known as tight geology, which is a great description. Because this layer here in this animation, and obviously this is very simplistic, but nonetheless it gives you a visualization of what we're talking about. In this layer here, this is the target geology. It's tight geology. In other words, it's extremely compact. And it's held on to its hydrocarbons for millennia. And now man, in his arrogance, says, yeah, but we've got a process that's going to release those hydrocarbons. So this tight geology has to be fracked to create artificial porosity. So it's the next stage of the process that is the core of the problem.
The perf gun is then pulled out of the hole. Next, because shale is tight or compressed, the well will have to be fracked. Known as hydraulic fracturing, this is a process where water, sand, and additives are pumped into the wellbore and down the casing under extremely high pressure. Water and sand make up over 99% of this frac fluid. The remainder consists of compounds commonly found in consumer products. As the mixture is forced out through the perforations and into the surrounding rock, pressure causes the shale to fracture. This creates a pathway connecting the reservoir to the well and allows the gas to flow to the well bore. Next, a temporary plug is used to close off or isolate the perforated and fracked section of the well bore, so that the next stages of the horizontal leg can be perforated and fracked.
Now that's what's called a multi-stage frac job, and in the interests of expediency and cost, there are companies like Schlumberger, my former company, and Halliburton, who will brag that they can do an 8-stage frac in one day. By doing it in one day, I can tell you, you're cutting some serious corners. But let's start to break this process down. We start off with the vertical well. Now this is a misnomer, because there is no such thing as a vertical well. The well is drilled with a drill string, and the motor, at the end of the drill string, drags the drill string in a increasing spiral. So what you've actually got is a massive corkscrew. When you put the casing down the well, the casing is looking for a vertical well, but it doesn't find one. So of course the casing has to distort as it's pushed down the well. This is why the spacers are so important, and this was a key issue in the Piper Alpha disaster and also the BP Deepwater Horizon disaster. Because if the spacers aren't properly located, then what happens is that the casing, of course, isn't in the centre of this spiral, it's over to one side. So what you end up with is cement that's maybe that thick one side and almost non-existent the other.
What's a spacer?
A spacer is what keeps the casing in the centre, or is supposed to keep the casing in the centre of the borehole. And basically, the way the spacers work is they're spring-loaded, So they're pumped down with the cement, down the casing. When they get to the bottom of the casing, because they open out, they spring out, and then they're forced up the side, up the annulus, by the cement as it's forced up the side of the casing. Now, with the Deepwater Horizon, in the section of casing that caused the problem, there was supposed to be 24 spacers, and they knew they were running the job with only 8. And then they're surprised that there was a blowout. It's cutting corners. So there's no such thing as a vertical well. The oil and gas industry accepts and acknowledges that the contamination problems are caused by loss of well integrity. In other words, what that means is basically the seepage from the geology into the well because the cement hasn't set properly, and of course it's finding its way up the cement, you know, the gas or the oil or whatever, it's finding its way up through these cracks in the cement and then breaching elsewhere into either other geological strata or worse, of course, the aquifers. Notice the terminology they used at the start. They said they drill below the deepest aquifer closest to the surface. The deepest aquifer closest to the surface. It's a total contradiction of terms, it's meant to be, because they're not getting anywhere near the deepest aquifers. In fact, there's a massive issue right now between the Mexican government and the US government, because the Mexican government know that there are phenomenal deep aquifers in the border area either side of the Rio Grande. And they have designated these aquifers as the water reserves for future generations. And they are now, rightly in my opinion, accusing the Americans of deliberately contaminating these deep aquifers by the fracking that's going on over on the Texan side of the border.